Good morning students. Today class we are going to discussing about the mean square value of output response. In last class we have seen that what is the system response and how to give the mean value as the input. Today class we are going to discussing about the mean square value of output response. For this one we have to consider the expectation of y square of t. Y square of t. Have to consider single y of t is a convolution of h of t and x of t. But here you can consider the square, you can writing the expectation of h of t, the convolution of x of t into, we can take in the one more combination, the h of t convolution of x of t. These are the ways you have to consider when you have to take in the mean square value. For that, I have to writing the expectation of for first value and the expectation of second value. Here, the first one is representing the convolution between h of t and x of t. Is a one pair combination, and the second pair combination is h of t and x of t. Here in this case, you have to consider tau 1, and in this case, you have to consider tau 2. But the formula is you have to make in the convolution, you have to writing its basic formula. Then you have to separate the integrals. Have to keep these integrals in one side, and you have to writing what are the terms in that equation. So you have to writing the separately. Those are x of t minus tau 1 and x of t minus tau 2. These two are the variables, and these two are not having any t parameter. That's why I'm writing separately. Then in next step, I have to applying the expectation on x terms. The x terms is having the delay of tau 1 and tau 2, and then these two is not having any time parameter. Here, this expectation of x of t minus tau 1 and x of t minus tau 2 is representing the time shift. The tau 1 and tau 2 is both are representing time shift, and this entire function, it is the shortest notation of autocorrelation function. Autocorrelation function. The autocorrelation function we are writing like this: the Rxs of t1 minus the tau 1 minus tau 2. That quantity you have to replace in that. It is representing the response of a system without applying the autocorrelation as a input. And coming to the next one. Here the response of a system, you have to see the autocorrelation, but here it is value of representation of mean square value output response. Coming to the next topic is the autocorrelation function. The autocorrelation function of output response. In that, you consider the basic definition of autocorrelation, that is RYY of y. You can consider y parameter. The y parameter is the output of our system. That's why you can consider RYY of t1 comma t2 is equal to expectation of y of t1 and y of t2. Then you have to elaborate the y of t1 and y of t2 in terms of h of t1 and x of t1 and h of t2 and x of t2, like this. What you can writing in terms of mean square value, the same procedure you have to apply here, the autocorrelation function output response. Then you have to write in the functions, either tau 1 and tau 2. Here also be, you can writing the how to follow the procedure in a mean square value. Then same procedure you have to applying here. Then you have to writing the RYY of tau is equal to Rxs of tau is a convolution of h of tau and h of minus tau. Here you can take in the convolution between h of tau and h of minus tau. It is representing this formula. Based on the even functions formulas, when we have to consider time shifting, those relations can be representing by using this one. This is the output. This output is only depending on tau parameter. It is independent on small t. Independent on small t. This is a response we are obtaining when not applying the autocorrelation is the input to your system. Now you can see the cross correlation. The cross correlation function of a output response. Output response. For that, you have to consider x of t is a WSS random process. Then the cross correlation function of input x of t and y of t. X of t is the input and y of t is our required outcome. The y of t we can obtain by taking the cross correlation. The cross correlation we are representing with Rxy of t comma t plus tau, that is equal to expectation of x of t into y of t plus tau. Then we can Splitting these terms, so what are the terms we are having in that expectation, how to writing x of t is outside of integration, and remaining is h of tau 1 and x of t plus tau minus tau 1 into d tau 1 is a normal function. Then you have to move this x of t1 and you have to separate what are the terms is high in the time parameter. Those terms have to writing one side and the remaining terms have to writing the another side. Then you have to apply the expectation on which terms is high in the t parameter. That's why I have to apply the expectation on x of t and x of t plus tau minus tau 1. Then you have to writing the h of tau 1 is outside of the expectation, which is the convolution. This one is representing the convolution of Rxy. We say Rxy of tau and h of tau. H of tau. Suppose you need to consider is Rxy of tau. Rxy of tau we have to representing is a Rxs of tau convolution of h of tau. Suppose you can consider the yx of tau, can also representing the reverse order, have to take the negative sign. Is Rxs of tau is a convolution of h of minus tau. Here you can take the order is Ryx of tau is equal to, you can represent is a minus 2 plus infinite is Rxs of tau minus tau 1 the h of minus tau 1 into d tau 1. Here from this equation we can set that x of t and y of t both are jointly WSS. Jointly WSS random processes. And Ryy of tau is equal to Rxs of tau, the convolution of h of tau and h of minus tau. And similarly you can writing Rxs of tau is equal to Rxy of tau and h of minus tau. And finally you can writing Ryy of tau is equal to Ryx of tau is a convolution of h of tau. This can representing the finalized output responses of when out applying the cross correlation function as input to your system. Here you can simply remember, you can write in the cross correlation function, then you have to representing this function as a in terms of convolution. The convolution product term, it can be representing the output response of your system. Coming to the next topic is the spectral characteristics of a system response. Up to now we are saying that is the time domain characteristics of a system response. Now we are going to discussing about the frequency response of a system. We can able to discussing about the frequency response of a system. We are having a complete idea about the Fourier transform. For that you have to consider x of t. Have to consider x of t is a WSS with autocorrelation function is Rxs of tau. It is applying to the LTI system. After applying to LTI system, the output response y of t is also WSS. You have to consider the input is a WSS. What are the response you have to obtain when not applying the input? The response is also be WSS. WSS means already we know that is a wide or weak sense stationary random process. Now the x of t and y of t is jointly WSS. How to treating as x of t is a WSS, the output response of a system is also be WSS. Then you can simply set that x of t and y of t both are jointly WSS. Now we can obtain the power spectral density characteristics of a output process y of t by taking the Fourier transform of a correlation function. We can obtain the characteristics of output response of a system. We can take in the Fourier transform on a correlation function, then you can easily obtain the spectral characteristics of a system response. For that we can take the power density spectrum of a response or output response. How to take the system, in the system x of t is a input, and its system function Fourier transform is h of omega, and the output is y of t. If the power spectrum of the input process is you can treating as s axis of omega, then the power density or power spectrum of a output is s yy of omega is equal to h of omega modulus square into s axis of omega. This is one of the important property. You have to use this property in problems. Coming to the next one, the spectrum bandwidth. Already you know that the bandwidth is a collection of band of frequencies. Otherwise, you can call it a band. Band is a collection. The collection of frequencies you can call it bandwidth. Here, the power spectral density is mostly concentrated at a certain frequency and it is decreasing at other frequencies. Here, the power spectrum is only concentrating at particular frequency, exact one frequency, and except that frequency, the value decreases. The bandwidth of spectrum having a significant frequency values. Generally, the bandwidth they are representing. Suppose I have to take one spectrum. In the spectrum, I have to take the 3dB line where the line can be cutting the graph. We can take the lines. In between those, I have to give the numbers of omega 1 and omega 2. The bandwidth is omega 2 minus omega 1. This is the formula I have to choose, I have to find in the bandwidth. In other words, the measure of spread of the spectral density, also called RMS bandwidth. Here, how much of spreading is there, the spectrum density you can call the bandwidth. Otherwise, you can, in other words, you can call it a RMS bandwidth. Those value we are defining with is a W square RMS is equal to integral minus infinite to plus infinite is the omega square is the S suffix xx of omega d omega divided by the minus infinite to plus infinite S xx of omega into d omega. This is a formula we have to obtain the spectrum bandwidth. Coming to the next one is the types of random processes. Here the types of random processes are classified based on the property of frequency. Based on the frequency parameter, we can able to do classifying the random processor mainly 4 types. Those are, first one is low pass random process, and the second one is band pass random process, and the third one is band limited random process, and the fourth one is narrow band. It's a narrow band random process. Here the random processor mainly classifying based on the frequency parameter, where you can using this random process. Spectrums, you have to using the spectrums of your random process. Why you have to using the spectral characteristics under random process. For examples of this classification is audio, video, and modulated waveforms. Now we can see the first category is a low pass random process. The low pass random process, we are able to define in that if its power spectral density is S xx of omega has the significant components within frequency band. Within frequency band, we can call that it is a low pass random process. The best examples of this low pass random process is baseband signals such as speech, image, and video. You can see the graphical representation of low pass random process. Here we can consider the spectrum. In this x-axis we have to consider omega. On y-axis we need to consider the spectrum. The power spectrum is SSN of omega. Here you have to take certain cutting voltage. The cutting frequencies is omega naught, here minus omega naught. In the spectrum, it is representing the power spectrum of low pass random process. Here the spectrum is cutting at higher values in positive and lower values in negative. And now to consider the bandwidth of the spectrum, had to choose the higher limit minus lower limit. It is representing the total limit of the spectrum. Coming to the second type of random process is band pass random process. Here the band pass random process, we are defining that its power spectral density is S xx of omega within the bandwidth. Within the bandwidth W, it not include at W is equal to 0. Here W is indicating the bandwidth. If the signal or a spectrum, if the spectrum is existing within the bandwidth, it doesn't having the value at omega is equal to or W is equal to 0. Here you can see here the graph. In that graph, I have to take two spectrums. The one spectrum is lying in a negative axis. and another spectrum is lying on positive axis. Here the spectrum is representing on x-axis is omega and y-axis is SSN of omega. Here the omega is representing the bandwidth and omega naught is representing the central frequency. Here each spectrum is having its unique bandwidth. At when I to consider at omega is equal to 0, the components is very less. The components is very less. Have to treating or we are neglecting those values at omega is equal to 0. This is the definition for the band pass random process. The examples of band pass random process is the modulated signals with carrier frequency of omega naught. Carrier frequency of omega naught. The another example for band pass is the noise over a communication channel. The noise over a communication channel. It is one of the model. It is one of the model of band pass random process. Coming to the next category, it is a band limited random process. Here each and every one it is interrelated. The band pass had to set to be band limited when its power spectrum components are 0 outside the frequency bandwidth. Outside the frequency bandwidth, the components of the spectrum is 0. When I have to consider band pass is a band limited, and it is also not including the W is equal to 0. Have to see the graphical representation, you can easily understanding. In the graphical representation, I have to consider omega on horizontal axis and SSN of omega is representing on vertical axis. But we have to represent in the spectrum on negative axis as well as on positive axis. It's having the bandwidth is omega and it is also having the bandwidth is omega. But the components are not existing outside the bandwidth. Outside the bandwidth, we can call it is a band limited random process. Here, the band limited random process had to extracting the narrow band. The narrow band random process is we have to explain that is the fourth category under the types of random process. The fourth category is a narrow band random process. A band limited random process said to be is a narrow band. Said to be narrow band when the bandwidth is lesser or very less. Very less to its band center frequency. The bandwidth is very small compared to the band center frequency. We can set that it is a narrow band random process. The narrow band is modeled as cosine function. The narrow band is modeled as cosine function. It is representing as is n of t is equal to a of t cos of omega naught t plus theta of t. In this equation, here n of t is representing narrow band signal. In that, a of t is representing the magnitude of his signal, and theta of t is representing the phase of random process. The phase of random process it is representing. Here, the graphical representation of this narrow band random process is this one. On horizontal axis, we need to represent the omega. On vertical axis, we have to representing n of t. Here, the signal is a very compressive nature. The compressive nature signal we have to calling it is a narrow band. Why? Because the total signal will be compressed. Here we have to represent its bottom values and higher values by taking the narrow band random process. Here, the representation of a narrow band had to take the equation, the general equation for arbitrary signals. And after taking the arbitrary signals, had to representing the narrow band signal as a function of cosine and sine functions. That is, n of t is equal to x of t cos of omega naught t minus y of t sine of omega naught t. In that, x of t and y of t both are in phase. And n of t is quadrature phase. It is having that. Here, the x of t is we are defining with a of t into cos of theta of t. Similarly, the y of t we are able to define is a of t into sine of theta of t. The relation between a of t and theta of t in narrow band equation have to writing a of t is equal to its magnitude. The magnitude is equal to the square root of x square of t plus y square of t is a, it's not a plus, it is a convolution. It is a convolution you have to treating, otherwise the convolution you have to treating in a square term is a product. It is a product we have to writing, that is x square of t plus, is a not a plus, it is a into y square of t, and the theta of t is equal to, it can representing the phase of narrowband random process. The phase of narrowband random process, it can able to define, it is a tan inverse, the tan inverse of y of t divided by x of t, y of t divided by x of t. Now coming to some of the properties under narrowband random process. Those properties are, the first property is, if n of t is WSS, that means the wide sense stationary, then x of t and y of t are jointly WSS. Here in this case, we have to treating the n of t is a WSS, is wide sense stationary random process. What are the values it can be including in that narrowband random process? Those are x of t and y of t are both jointly WSS. And if n of t has zero mean, that is expectation of n of t is equal to 0, then what are the individual values of their x of t and y of t expectation values is also be 0. Had to see the mean square values of random process. The mean square values of random process is equal. Those are expectation of x square of t and expectation of n square of t is equal to expectation of y square of t. These all quantities are equal under narrowband random process. Here both x of t and y of t have the same autocorrelation functions. Under narrowband process, the x of t and y of t have the same autocorrelation function that can be representing with rxy of tau is equal to ryy of tau, rxs of tau is equal to ryy of tau. And now to consider the cross correlation function. Cross correlation function we can representing is rxy of tau is equal to ryx of minus tau. These are the properties we are having under narrowband random process. Up to now we have to discussing about is a complete fifth unit.